From the lab, you may have noticed that if your tension force was on the vertical axis and the weight, the gravitational force, was on the horizontal axis, both measured in newtons because that is the unit for force, and your data points were nice and lined up, and then your best fit line through the data points looks like this. And the equation for your graph probably looked like force tension is equal to 0.5 times Fg. Now remember, it may have been reported as 0.5x on the graph, but remember this is an understood equal to y, and on our y-axis we have the tension force, so I'm going to substitute that in, and on our x-axis we have the gravitational force, so I'm going to substitute that in. Now when it comes to our object that was being pulled, there was a tension force to the right, force tension, and there was a force of friction to the left. There was a weight force down and a normal force up. And the weight and the normal are equal to each other. And if it was not going to move, and if this force was the maximum force just before it moves, then those two forces were equal to each other as well, the friction force and the tension force. So if I take my equation and I know that this system is in equilibrium, and if it's in equilibrium, then the sum of the forces has to equal 0, which means that our tension force minus the force of friction, the minus comes from the fact that it's pointing to the left, they would add up to 0, and that would be my sum of the forces, in this case in the x direction. Now, that means that my tension force is equal to this force of friction. If I do the same thing for the y direction, summing the forces vertically, it's also in equilibrium, so balanced. The sum of the forces in the y direction would equal the normal force, which is up, minus the weight, which is down, pointing down, equals 0, which means that the force normal is equal to the weight. So if I have this equation up here that says the tension force is equal to 0.5 times the weight, I could substitute in the friction force for my tension force and my normal force for the weight. So just making a substitution here, we get that the force of friction would equal 0.5 times the normal force. And we're defining both of these as being forces from the surface onto the box. So we're looking at how the surface is interacting with the box. Now, if we think about what was happening in our lab, we were keeping the box from moving, so it was remaining in a static state. So static means not moving. If you applied or changed the tension force to be too great, you may have noticed that the symbol changed from a S to a K. So the alternate is that we can have a force of friction kinetic is equal to some number times also the normal force. If we go back and experiment again, but this time look for the force needed to just keep it going at a constant rate, we would find that there would be a different number, a different slope here. Now each one of these numbers is particular for the type of surface. An icy surface is very slippery, so it doesn't take as much force to get it to move. A rough sandpaper surface would take more force. So we have these two different frictional forces that act on our objects. So we can have the force of static friction, and that will be equal to a coefficient. Now remember, the word coefficient means number in front of. So the coefficient of friction, and we're going to use this Greek letter mu. So I'm saying mu, and if I was drawing on kindergarten paper, I would draw a mu to look like this. So that would be mu static. I'll put a little s here. And then this would be the force normal from the surface onto the object. And similarly, our force friction kinetic will also be mu k times force normal. Now it always takes more force to get something going than to keep it going. And so mu static is always a greater number than mu kinetic. And this equation up here for our static friction, now remember in the simulation we could see that we applied a tension force, and let's say for example our box was here and we applied a tension of 10 newtons, and there was a backwards force of friction, and which was also 10 newtons, and there was no movement. Then we'd increase it to 20 newtons, and so the vector would get bigger and our friction force would get bigger. And then we would increase it to 30 newtons, and then this one would also get bigger again. And then maybe we jumped all the way up to 40 newtons, and suddenly we saw that there was no force of friction and only a smaller force friction kinetic. So what this tells me is that my force of friction static is a responsive force. It's going to respond to the amount of force that we're applying until it can't hold any more. So really, our force of static friction is equal to or less than mu static times force normal. So the maximum static friction is what we were actually determining in our lab. So this is our equation for our frictional forces acting on an object.